Hi everyone. So today's topic is about greedy algorithms. Okay, so in this section we will learn how to approach various problems using the greedy strategy. Okay, so let me give you a brief overview of greedy algorithms. So first of all, greedy algorithms are the most intuitive algorithms. Okay, so most of the times, given any problem, the first algorithm that comes in your mind is actually a greedy one. Okay, so the first thing to note is they are most intuitive algorithms, and sometimes this intuition may be wrong also. Okay, for example, in a DP problem also you generally come up with a greedy algorithm. Okay, so that generally is not correct. So we will look at what type of problems you can apply a greedy algorithm. Okay, so the first solution that comes to our mind most of the times is a greedy solutions. So greedy approaches are quite simple and they're easy to understand and formulate. Okay, and most of the times it's related to mostly the question is about sorting. Okay, or you want to pick the largest element or you want to pick the smallest element, something like that. Okay, so proving part may be difficult. Okay, so mathematics it might be difficult. So given you are participating in an online round, you do not need to go into the mathematical or the proving part, but what you can do, you can make some test cases and see whether greedy will work or not. Okay, so that is something I would advise you instead of going into a mathematical kind of a proof. Okay, so what does a greedy algorithm do? So greedy algorithm always makes a choice that looks best at the moment. Okay, what is the, suppose I'm standing at this particular point and I have three options to go to the next step, so which option I will pick? Okay, so if I pick all the options, it will be brute force. And if you feel, uh, or it can be DP also. Okay, so if you pick all the options and see what is the best option, then either it will be a brute force method or it will be a DP based method. But you hope that by choosing this particular option, I will reach the answer. In that case, we will say, okay, we will choose a option that is a locally optimum option, and by choosing a locally optimum at each step, I will end up at a global optimum. Okay, so this is the most important thing that we have to learn in a greedy problem. So I will give you one example in this case. Now let me give you a very common example that I generally discuss. So let's say you want to make a change for Indian currency. Okay, you want to make a change for rupees 39 using minimum coins. Okay, using minimum number of coins. Okay, so now there are multiple ways to approach this problem. Okay, so first option, the first thing that comes in our mind is, if I want to make a change for rupees 39, what I will do, I will pick the largest coin or note that is less than 39. Okay, so obviously I know from 39 I can reduce this problem to 19 rupees by picking a 20 rupee note. Okay, because 20 rupees is the largest note that is less than 39. From 19 I can say I will pick a 10 rupee note because it's the largest and less than 19, and I can reduce this problem to 9 rupees, and then I can pick a 5 rupee coin. I can reduce this problem to 4 rupees. I can pick a 2 rupee coin and I can reduce it to 2 rupees. I can still pick a 2 rupee coin and I can reduce this problem to 0 rupees. Okay, so this is how we can make the change. So we can say 20 plus 10 plus 5 plus 2 plus 2. So that is what makes 39, and effectively we need 5 coins. Okay, so this is the greedy way of thinking. Okay, so at each step we are picking up one option that we see is the locally best option, and by doing it at every step we are ending up at a globally optimum answer. Okay, you cannot make a change for rupees 39 in less than 5 number of coins. Okay, so what would be the other way of thinking this problem? That is the, let's say, brute force way or the DP way. Okay, so the other way would be, you can say from 39 I can have multiple options. If I pick a 1 rupee coin, I can reduce it problem to 38. If I pick a 2 rupee coin, I can reduce this problem to 37. If I pick a 5 rupee coin, I can reduce this problem to 34. Okay, So if I pick a 10 rupee coin, I can reduce this problem to 29. Or if I pick a 20 rupee coin, then I can reduce this problem to 19. Okay, and then further you will evaluate these nodes. Okay, and it would be a very large tree. Okay, and then you will have an optimal answer for each of the node. Let's say this is A, this is B, this answer is C, this answer is D, this answer is E. Okay, and then you will say, okay, I will find out the minimum of A, B, C, D and E, and I will add 1 to it. Okay, and it is also possible that some of the nodes have the same value. For example, if you are making a 19 here, or let's say you are making a 18 here, it's also possible that you are making a 18 here. Okay, in such problems where you will have overlapping sub problems, you can obviously optimize them using dynamic programming. Okay, so we also have a DP based solution to coin change problem, but especially for Indian currency. Okay, you will see that greedy approach works well, and you won't find even a single test case on which a greedy approach will fail for Indian currency. Okay, so we are talking about Indian currency. Okay. So what will happen here? You are directly going into this path. Okay, you are saying, okay, no, I will just pick the largest coin, that is 20, and I will just choose this path. So out of multiple options, you are saying, no, I will pick the locally optimum option, because this option allows me to reduce my sub problem to the smallest problem. So this choice, choosing this, is a greedy choice. Okay, and finding out all the sub problems, evaluating them, will be a brute force method. Okay, or you can say it will be a DP if you handle the overlapping sub problems case. Okay, so clearly if I talk about which algorithm would be faster, clearly we know the greedy one will be faster. Okay, and DP one will be slow. Okay, but then you might ask, why don't we apply greedy to all DP problems? Because greedy might not give you an accurate answer always. Okay, so this is always accurate. This will always gives you an accurate answer. Okay, but in this problem, greedy will give you a correct answer, and DP will also give you a correct answer, but this would be much faster than the DP based method. Okay, so what we can do is, so let me give you one example where you will see greedy will actually fail. Okay, so for example, you go to a different country where the coin denomination is like this. You have a 1 rupee coin, you have a 7 rupee coin, and you have a 10 rupee coin. Okay, and let's say you want to make a change for rupee 15. So what you will do, if you apply a greedy approach here, you will say, okay, from 15 I can reduce my problem by picking a 10 rupee coin to 5, and to make 5 I will just have a 1 rupee coin. Okay, so from here I will reduce to 4, 3, 2 and 1. Okay, so effectively you will end up having 6 coins as a change. But if you apply some other approach, maybe a DP based approach, so from 15 you can reduce it to 14, and from 15 you can also reduce it to 8, and you can also reduce it to 5. Okay, so greedy says I will pick this path because this looks me the most optimum path, but a DP based solution will say, okay, let's try out all the paths. Maybe you evaluate this path. Okay, from 14 you can reduce to 13, you can reduce to 7, and so on. From 7 you can also reduce to 6, you can also reduce to 0 by subtracting 7. Okay, so clearly if you have a look at this path, it just uses 3 coins. Okay, and that is 7 plus 7 plus 1, that is equal to 15. Okay, so this is an example where you will see the greedy strategy actually fails. So greedy fails, so you have to go up with a DP based solution in this case. Okay, so here we can see that by choosing a local optima, we don't end up at a global optima. So this branch is a globally optimum branch. Okay, So I hope you got a basic idea between DP and greedy, and what type of problems you will apply a greedy strategy. So we'll see more problems in the next video. Hi everyone, in this video we will discuss the greedy coin change problem solution, and we will just discuss the implementation because we have covered the logic in the greedy algorithms. So the question is, you want to make a change for rupees 39 and you want to do it using the Indian currency. Okay, so we have seen we will first pick a largest node, that is 20. So for that we can use binary search, and we are given this coins array. Okay, so I can say, okay, index of the largest number, that is greater than 39, is, let's say, 20. So I will use upper bound function because it will give me a number that is greater than 39. Okay, so we will get a number greater than 39, that is 50. And if I get the index of 50 and if I subtract 1, I will get the index of 20. Okay, so we can use upper bound on the coins array. So I can say coins plus n, and the amount for which I want to find the upper bound is money. Okay, and what I need to do, I can say while money is greater than 0, let's find out the index of a number which is just less than the or equal to the given amount. Okay, so this would give me the index. Okay, so this will actually give me the address, and if I subtract the base address of the array, that is minus coins, I will get the index. Okay, so maybe you can just do cout coins of index, maybe followed by a plus, and then you can say reduce money by this amount. Okay, so money equal to money minus coins of index. Okay, and finally the number of times this loop is running is my answer. Okay, because we want to count the number of coins. Return answer. Okay, so we can call this function make change, and here I can give coins. N is number of coins, that is t, and or maybe just make it as money. I will accept the input from the user, and this function will give me how much change I want to make. Okay, so build is successful. Let's try to run the code. Okay, let me give 39. So you can see it's 20 plus 10 plus 5 plus 2 plus 2, and maybe you can just do cout these many coins are needed. Okay, something like this. So that will give you both the number of coins and the type of coins. Okay, so let me give 39. It says coins needed is okay, so this is 5 actually, so we can just skip this. Okay, so you can see 5 coins are needed, and if I give, let's say, 110, then I need 2 coins, a 100 rupee coin and a 10 rupee coin. Okay, so that's it, and you can see how easy it was to implement this uh, greedy algorithm. And we also made a use of upper bound instead of doing a linear search, and this makes our implementation more optimized. So thanks a lot. We will see some more interesting problems from the next video. Hi everyone, in this video we will discuss another problem. It's called busy man from Sponge. So the problem says you are a very busy man and you have a big schedule of activities, and this is actually a very popular problem, also goes by the name of activity selection problem. Okay, so your goal in this problem is to do as much activities you can do. So what you're given there are n activities, and you're given the starting and the ending time of different activities. Okay, So it's like this. You're given n number of activities, and you have, for each activity you know the starting time and the ending time. Okay, so for example, there is an activity in which you have to go for a date with a crush, okay? And this goes from 1 p.m. till 5 p.m. This is known to you. And there is another activity in which you have a coding contest from, let's say, 1 p.m. to let's say 8 p.m. Okay. So similarly, there are other activities like watching movie, play Dota, study for exams, sleep peacefully, and so on. Okay. So your goal is you want to do as much activities as possible. So how you are going to approach this problem, you have to think. Okay. So generally you need to do some kind of criteria. You need some criteria to pick a activity. Okay, so generally people have come up with different ideas. So maybe you will see that, let's say, one person says, okay, I will do an activity that starts first. Okay, so maybe given this data you can sort it according to start time. Okay, the activity that starts early, I should do it. But is it the right thing to do? No, because it's possible that there is an activity that starts at 1 p.m. and it ends at 12 p.m. So we should also focus upon uh, how long is the activity. Maybe we can do a sorting of all the activities, maybe do according to the duration. Okay, that is another idea in our mind. So start time definitely is not the useful thing. Duration, so let's pick up those activities that takes 1 hour or 30 minutes or 20 minutes to complete. But is it the right thing to do? Let's take one more example. Okay, I say there is an activity from 6 to 7 p.m. that is only of 1 hour. So maybe I'm planning to sort according to the duration. Okay, but suppose there are two more activities in this graph which are like this. Okay, so if this happens, you say, okay, I will pick this activity because it is the shortest activity. You won't be able to complete these two activities. So obviously this is a wrong solution, because if you skip this activity you will be able to do these two activities. Okay, so obviously we cannot sort according to the duration. So third thing that in our mind is, let's sort this list of n activities according to end time or the finishing time. So maybe I will pick that activity which finishes early. Okay, so if an activity finishes early, it will allow more time for the remaining activities to be done. Okay, so this is a greedy thinking. Okay, so this is a greedy thinking, that if I complete an activity as early as possible, okay, according to the finishing time, then I will have more room for other activities that I can do. Okay, so let us sort this list according to the finishing time. So the first activity that finishes is dating with crush. Next activity is watching movie. Third activity according to finishing time is coding contest. Fourth is Dota. Fifth is study for exam, and sixth is sleep peacefully. Now we have to see, if we have sorted this list according to finishing time, then what is the maximum number of activities we can do. So obviously we will pick the first activity because this we can certainly do. The next activity, that is watching movie, we will have to see if we are able to do this activity or not. So we will be only able to do this activity because only if the start time of this activity is greater than finishing time of previous activity. Okay, so obviously we cannot do this. Let's go on the next activity, that is coding contest. We cannot do this because it also overlaps with the first activity, so this goes off. So next activity is play Dota. So can we do play Dota? Yes, obviously, because it starts after the first activity has finished, so we will do this. Okay, and finally, can we study for exam? No, because it overlaps with the previous activity. And finally, can we sleep peacefully? Yes. So you are able to solve this problem, and clearly you can see there are three activities that you can do. So you have a thug life, you go on the date, you play Dota, and you sleep peacefully, and that's it. Okay. So what we will do in the next part is we will implement the same using C++ code, you can also try this code yourself. Okay, so thanks a lot, see you in the next part. Hi everyone, in this video we will see the implementation of the problem busy man. So let's see the input format. Okay, so input contains multiple test cases, and for each test case we know the value of n, the number of activities, and for each n we have a start time and a end time. Okay, so we have three test cases, three activities in the first test case, and followed by this. Okay, so let's jump into the code editor. Okay, so problem is busy man. Okay, so I have done with the few libraries that I would be needing. So let's write the main, and first thing that we need to input is the number of test cases. We also need n, start and end time. So let's take input test cases. For each test case we need to read the value of n, and for each n we have to take input two numbers, start and the end time. Okay, so that we will take input, and what I can do, I can make a vector of pair. Okay, so let's say I have a vector of pair of int comma int, and let's call it as v. Okay, so after each test case I should also clear my vector so that I can store the data for the next test case also. Okay, so what I will do, I will just push back these values into a vector. So these go into the vector, and here I will build my activity selection algorithm. Okay, so first thing is we need to sort all the activities according to the finishing time. So I can say sort v dot begin, v dot end, and I need to define my own compare function. Okay, so I can say bool compare, and here we will be comparing two pairs. So pair of int p1 and pair of int p2. Okay, so given two activities p1 and p2, we want to compare based upon the finishing time. So I can say return p1 dot first less than, sorry, p1 dot second, because the first value is the start time and the second value is the end time. So p1 dot second is less than p2 dot second. So that's my compare function. Okay, and now what I can do, sorting is done using the custom comparator we have written, and now we can start picking activities. Okay, so first activity we will always pick. So I can say the number of activities that I have is, let's say, is 1. So first activity I will always pick, and the finishing time of the first activity will be v of 0 dot second. Okay, and I will iterate over remaining activities. So for int I equals to 2, I less than n, I plus plus, and if I see the finishing time of the next activity, that is if v of I dot second, sorry, if the starting time of the next activity, that is dot first, is greater than equal to the finishing time of the last activity, then I can do that activity. Okay, so I can update the finishing time as v of I dot second, and I can increment my count by 1. So result stores the number of activities that I can do. Otherwise I will just move on to the next activity, and for each test case I will just print what is the value of result, and I will clear my vector. So I think this should be okay. Let's try to run our code on the test cases given by the sponge. Let me just copy this. So I'm getting the answer as okay. Let me give it one by one. Okay, so let's just do it for one test case. So I'm getting this answer as 2. Okay, sorry, this should be I equal to 1. That's a mistake because indexing starts from 0 and we have seen the 0th activity. So we'll start from the second activity, okay? So for this test case, the answer should be 3 and we are getting 3 as the answer. So let's try to submit this code on Spotch and see. Let's submit this code. Okay, so this should be okay, and I hope you will be able to solve this problem now, and the code is absolutely fine. Okay, so I'm not logged in, so that's fine, but this code is fine, and you can see this is running for the sample test cases as well. Okay, so that's it for this video. See you guys in the next part. Hi everyone, so we will be looking at a very simple problem this time. It's called connecting wires. So the problem is like this. There are n white dots and there are n black dots, and all of them are equally spaced in a horizontal line. Okay, so you want to connect each white dot with any one black dot using a wire, and your goal is to minimize the total length of the wire that is needed. Okay, so in the input you will be given the positions of the white dots, and you will be also given an array that contains positions of the black dots. Okay, so you will be, let's see one example like this. Okay, let's say this is a white dot, this is another white dot, and let's say this is another white dot, and let's say we also have okay, let's say this is a white dot and these are the white dots, and let's say these are the black dots. Okay, something like this. Okay, so all of these dots are equally spaced. So white dots are at coordinates, let's say 1 2 3 4 5 6. So the coordinates of white dots are, let's say, 3 4 and 1, and black dots are at 2 5 and 6. Okay, so you are given these coordinates. So you want to connect each dot with each blue dot with each green dot. Okay, with any one green dot using some wire. Okay, so now the question may be, okay, maybe let's connect this with this, and let's connect these two. So this is one way to connect these dots. There can be other ways also, and let me connect this one with this, and this one with this, and this one with this. So this is another way of connecting these dots, and as you can see, total wire that is needed is 1 plus 2 plus 2, that is 5 units. Okay, so you need 1 plus 2 plus 2, that is 5 units of wire. And maybe you can think of other ways, but if you want to minimize the total length of the wire. Okay, so if you want to minimize the total length of the wire, then the ideal approach would be a greedy approach. What you need to do, you actually have to, for each blue dot, you have to find the nearest green dot. Okay, so connect the white with the nearest black. Okay, with nearest black. Okay, so that would make sense, because if you try to go farther away, that will increase the length of the wire, and it's not possible that if you connect this one with a dot which is farther away and you connect these one, it will not give you a shorter length. Okay, you can try making different examples. So this may be also one of the solution, but it will not reduce the length if you do something other than this. Okay, so goal is here to connect each dot with the nearest black, and that is a greedy approach. You can make different test cases, and you will see that this actually is true for all possible configurations. Maybe if I have a green 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 followed by a blue 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 dot, something like this, then also if I just connect this one with this one with this, and this one with this will give me the minimum length of the wire. Okay, or if I have something like this, let's say the alternate ones. Okay, let's say I have two dots here and I have one dot here, then also you will see that if you connect these two and these two, they will give you the minimum length of the wire. Okay, so what you need to do, you need to sort this array. Okay, you need to sort this array, and after sorting this will be 1 3 4, and after sorting this will be 2 5 and 6. So you will connect these two and these two. So this will require one unit, this will require 2 unit, and this will require 6 minus 4 2 unit. So you just sum it up, subtract these and sum it up, and this will give you the minimum length is 5 units. Okay, so that's it, and this is how easy it is to solve this problem. And the coding part, I think we can skip, because it's a simple sorting problem. Okay, thanks a lot, see you guys next video. Hi everyone, so in this video we will discuss one problem that's based from Spodge. It's called biased standings. Okay, so it says there is a competition in which you want to uh, in which each team will be able to enter a single positive integer, their preferred place in the rank list. Okay, so there is a competition and there is a leaderboard, and each team wants a specific rank. Okay, so there is a team X which says, oh, I want to get a rank 5 in this competition. There is team Y which says, oh no, I want to get a rank 1 in this competition. Okay, so you have to take all these preferences into account, and at the end of the competition you have to simply announce a rank list. Okay, so we actually have to create a rank list of these teams. Okay, so there are n number of teams. Okay, and depending upon their preferences in the rank list, we have to satisfy all of the requests. Okay, but it is possible that we won't be able to give a desired rank to every team. So for that, what we may do is, uh, we will find out the distance between their preferred rank list and their actual rank. Okay, so some team was asking for rank 7, and let's say we give him rank 5. So this difference is called badness. Okay, and sum of badnesses of all teams is the total badness. Okay, so total will be summation of all badness. So given the team names and their preferred placements, we have to find a rank list with minimum possible badness. So let us see one example to see this further. Okay, so for example, there are two test cases, and in the first test case there are 7 teams, and these are the team names and these are the expected ranks. Okay, so if we want to minimize the total badness, we should assign a team a rank that is closest available, that is closest available. Okay, so if we have 7 teams, so we know in the beginning we have 1 2 3 4 5 6 7 ranks available. So we start allocating these teams the closest possible rank. So we give team 1 the rank of 1, so rank 1 goes to noobs. Okay, the next team that we should give is this. So we can give second rank to ilamas. Okay, and rank 3. So no, this we should not do because there is also a team which is asking for rank 1. Okay, so no, we should, what we should do, we should sort these. Okay, we should do the sorting. So after sorting, what we will get, we will get 1 1 2 2, and we have 5 7 and 7. Okay, so this is the uh, rank list after sorting. And as you can see, if you just take the absolute value, this will actually give you the badness. Okay, so for this the badness is 0, for it is 1, it's 1, it's 2, it's 0, it's 1, it's 0. So total badness is 2 plus 1 plus 1, that is 5. So this is the minimum possible badness, because by doing sorting we are able to assign a rank to a team that is closest available to that, for that particular team. Okay, so let's see if the answer is 5. So yes, the answer is 5. Okay, so clearly this becomes a sorting problem now. And we can also, okay, so let's also see. Okay, so I don't know what would be the value of n, so I can do it sorting in n log n time. That is one way. If I use inbuilt sort function, or that uses something like a merge sort. Okay, or a quick sort. Okay, but since you have ranks, in a particular range 1 to n. Okay, so we can also use something like a counting sort. Okay, we will use a counting sort based implementation that can solve this problem in order and time. Okay, so let's have a look at the implementation using counting sort. Okay, so what we will do in counting sort is, we will have an array. Okay, and we will maintain okay okay so what we will do, we will put these into these buckets. So we have buckets from 1 2 3 4 5 6 7. Okay, and we have the first team. Initially the count of each bucket is going to be 0. Then we see, okay, there is a team which has asked for rank 1, so we increment this count by 1. We have a team which has asked for rank 2, we increment this by 1. We say there is another team with rank 2, so we make it as 2. There is another team which has rank 1, so we make this count as 2. So we are updating the frequencies. So we make it as 1, we have 7, we make it as 1, we have another 7, we make it as 2, and rest all buckets are zeros. Okay, so in the beginning we can see the rank that is available is 1. We have not allocated this rank. So what we do, we pick a team. Okay, so this is, teams are now added into these buckets, and adding has taken order and time. So we pick a team 1 from this bucket, and we say the available rank is 1, so we give it this rank, and this contributes a total badness of 0, and this count is reduced by 1. So the next available rank will be incremented by 1, that is 2, and we pick one team out of it, and we say, okay, you will get a rank 1, so this gives us a total badness of 1, and this count becomes 0. So we go on to the next bucket. We pick a team 2, available rank is 2, and this team has asked for a rank 2, so this contributes a badness of 0, so we make this as 1. So we pick another team from this bucket, we make it a 0. It has asked for a rank 2, available rank is 3, so this contributes a badness of 1. We go to next, we pick this team, it has asked, available rank is 4, and this team has asked for a rank of 5, so this contributes a badness of 1. We make it 0. We go to the next, and then we have a team which has asked for a rank of 7, So this contributes a badness of 2 and we make it as 1. Okay, and now the available rank is 6. We pick a team and okay, so okay, small mistake here. This should have been 3, this should have been 4, this should have been 5, this should have been 6, and this should have been 7. Okay, so this is 0, this is 1, this is 0, this is 2, and this is 1. Okay, so now you can see this total badness 1 plus 2 plus 1, that is 5. This is also 1. Okay, so this is now 5. So this is how we can actually use uh, something similar to counting sort to solve this problem in just order n time. Okay, so the coding part is easy. I think you will be able to implement the code yourself and submit it on the spot. Okay, so you have to do it yourself. Okay, so that's all. See you guys in the next question now. Hi everyone, so in this video we will discuss the implementation of biased standings, and we will use the optimized approach that is based upon counting sort. Okay, so let's see the implementation. So first of all, I need to take input the number of test cases, and for each test case I need to reset this frequency array to 0. So I can use memset array 0 and size of array. Okay, and sorry, so after that what we can do, we can take input uh, the name of the team, and right, so for each test case we can take input the name of the team and the rank that particular team is expecting. So let's say scene name, and sorry, first of all we take input n and the rank. Okay, so scene n, then we can say scene name and the rank. Okay, sorry, this should be done for n number of teams. Int I equal to 0, I less than n, I plus plus. Okay, so I put a for loop so that I am able to process the rank and the name for every team. So I can just remove it. Okay, so once we know the name and the rank, what we can do, we can say in the frequency array for that particular index I will increment it by 1, because there is one team which has asked for a given preferred rank. Okay, so this is the preferred rank. Okay, and now we can use our greedy approach that assign the team nearest rank available. Okay, so we can start giving ranks from 1. So let's call it as the rank that we are giving, let's call it as the actual rank that we are going to give. I can say for int I equal to 1, I less than equal to n, I plus plus. I am going on every bucket, and I can say while this is not empty, while array of I is not empty, what I will do, I will maintain a sum. Okay, so let's make a variable sum that is equal to 0. I will say sum plus equal to the absolute value of my actual rank that I'm giving and the position I. So that is a given team that we are popping out has asked for the ith rank, and we can do array of I minus minus, that we are removing one team out of that particular box, and we should also do actual rank plus plus, so that for the next team this rank is not available but the next rank is available. And here we can just do cout sum and endl. Okay, so that should be it. So let's build the code. Okay, let's include the file called cmath. Okay. Mm, okay, let's make our own function. Okay, so int abs, int I, int j. So I can say return I, if I minus j is greater than 0, then return I minus j, else return j minus I. Okay, so we can do it like this. Okay, and let's try to run this code on a single test case. Okay, so we are getting a final answer as 5, which means our solution is correct. Okay, so that's all. See you guys in the next. Hi everyone, in this video we will discuss one very interesting and challenging problem from Swatch. It's called load balancing. Okay, so let's have a look at the problem statement. So it's given that there are n number of processors that are available. Okay, okay, so you have n number of processors. Okay, you can treat this as a array of size n, and each processor is numbered between 1 to n, and they are used to process independent jobs. Every new job is assigned to an arbitrary processor. So there are n number of CPUs, and each CPU has some random number of jobs to execute. Okay, let's say like this. And sometimes a processor may be assigned too many jobs, while other processors have a relatively light load. For example, this processor has a heavy load because it has to execute 6 jobs, and this processor has a light load because it has only one job. So in this case, the whole system has to undergo rebalancing. So let us see what is this task of rebalancing. So rebalancing proceeds in rounds. In each round, every processor can transfer at most one job to each of its neighbors on the bus. Okay, so they are connected serially on a bus. Let's say you have a processor like this. Okay, so they are connected. In each round, the processors that are in the middle, they can transfer one job to each of its neighbors. So for this processor there are two neighbors. For this processor there is a one neighbor. For this processor there is a one neighbor. So neighbors of the processor are I minus 1 and I plus 1, as we just saw. And the processors which are at the end have only one neighbor. Okay, so for this processor, this is the only neighbor and this is the only neighbor. The goal of the rebalancing is to achieve all the processors have same number of jobs. So firstly you have to check if it is possible to have equal number of jobs on every processor. For example, in this case, total number of jobs is 1 plus 4 plus 1, that is 6, and average number of jobs per processor should be 2. So one round of after one round of rebalancing, what will happen? 4 will transfer one job to each of these processor, and you will see the state of the array will become something like this: 2 2 and 2. So this is the goal of rebalancing. Each element of the array should be same. Okay, and you have to tell how many rounds it will take. So you're given the number of jobs initially assigned to each processor, and you have to find minimum number of rounds needed to achieve the state when every processor has the same number of jobs. And if this is not feasible, if this is not a integer, then you have to print no state is possible, or you have to print -1 in such a case. Okay, so we will see some examples. Okay, let's see the first example. Okay, so in the first example, you are given there are um, three processors. The first one has a job 0. Okay, it's like this. Okay, so this is our initial state. The final state should have 34 in each, because if you just sum this up, so it becomes 102 divided by 3, and this is equal to 34. So finally each processor should have 34 jobs. Okay, so let us see what can happen in each round. Okay, let's talk about after first round. What you can do, you can say, okay, we are going to transfer one job here, one job here. So it will be like this: 197 and 4. After second round it will be like this: one job here and one job here. So it will be 2, 95 and 5. And let's keep on doing this for, let's say, 30 rounds. Okay, so after 30 rounds, if you keep on giving two jobs, so it will be 99 minus 60, that is 39. This will be 30 and this will be 33. Okay, so this is the state after 33 rounds. After 30 rounds, let's talk about 31st round. Okay, so in 31st round also you give one job here, one job here, so it will be 31, 37 and 34. Now you can see this block already has 34 jobs. So for further rounds we won't be giving any new jobs to this processor, we will be just transferring jobs this set, because there is a deficiency of jobs. So it will be 32 and 36 and 34. Let's talk about 33rd round. It will be 33, 35 and 34. And let's talk about 34th round. So finally in the 34th round it will be 34, 34 and 34. Okay, so that's why you can see the answer for this case is 34, because we needed 34 rounds to do this task. Okay, and for the next test case you can see there are 99 jobs and you cannot divide it with 2, so the answer is -1. Similarly you can have for other test cases as well. Okay, now how do we apply a greedy strategy? Okay, we have to think how this question can be solved using a greedy approach. That's what you need to think. Okay, so take your time and try to think what you can do. Okay, so the first hint is that you first need to calculate what should be the final load on each processor. Okay, calculate final load on each processor. So this is actually easy. Okay, so that for that you just need to find the sum of the array divided by number of elements of the array. So this is what you need to see, and if this is not an integer, then you can simply say this is the easiest case. My answer is -1. But suppose you know the final load. Okay, so then for each position of the array, okay, so there will be some cells which would require extra jobs, and there would be some cells which would have surplus jobs. Okay, so let's say these cells are surplus and these cells are deficient, and if you want to make everyone as equal, maybe let's say dot 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 dot, and what you need to do, you are actually going to transfer jobs. Okay, and we also know that this transfer is going to happen across um, from one part of the array to another part of the array. Okay, so let's say this whole is one array, and if I just try to break this array at a ith index, I know some of the jobs will be transferred from this part to this part, or I know some of the jobs will be transferred from this part to this part, and also I know there would be some transfers which would happen internally inside this array. Okay, so let me give you one more example. Suppose let's say this part has 10 jobs and this has 0 0 jobs. Okay, so if I just think about this boundary, you will see there would be a overall transfer from this part of the array to this part of the array. Okay, so 10 will give one job to this, and it will give one job here, it will give one job here, and so on. Okay, so there would be some internal transfers as well. So what I am trying to say here is, suppose there is a transfer of, let's say, so finally there should be 4 jobs in each cell, so finally there should be 8 jobs, and in this part of the array there should be 12 jobs. Okay, so which means if the initially all the jobs are 0, you are transferring 12 jobs of the from this boundary. Okay, so from this boundary you are transferring 12 jobs to this part of the array. So what I'm trying to say here is, suppose there is a transfer of 12 jobs, and internally there is a transfer of 6 jobs. So these two operations can happen in parallel. Okay, so they can happen in parallel because uh, processors can work in parallel. Okay, so okay, so what I am trying to say here is, you have to actually find out what is the maximum load that is getting transferred between two parts of the array. Okay, maximum load that is getting transferred between two parts of the array. Okay, and what are the two parts? So we have to try for every part, we will break at every possible I starting from 1 to n minus 1. Okay, so we'll try to create a partition from 1 to I, that is one part of the array, and other part of the array will be from I plus 1 to n, and we will try to find out what is the maximum load that has to be transferred from one part of the array, that is the donor part, to the other part of the array, that is the acceptor part. Okay, and it will be, finally the answer would be the maximum of all such loads. So let me give you more examples to make this thing clear. Okay, so let us see, we have array where we have this as our input. So finally we know the final state would be like this, 4 4 4 4, and now if we just see what will happen in each round. Okay, so let's say after the first round this gives a job here, this gives a job here, so it becomes 5 1 1 9. Let's talk about second round. Okay, so it will become 4 2 2 8. Let's talk about next round. Okay, now this processor will not give a job because it requires 4 jobs and it is already at 4, so 8 will give a 1 job here, and maybe 2 gives a 1 job here in parallel. Okay, at the same time, so these two transfers are going to happen, so it becomes like 4 3 2 and 8. Okay, again in the next round 2 gives a job here and 8 gives a job here, so it becomes like this, 4 4, and we have 2 and 8, 2 and 6. Okay, and then again in the fifth round it becomes like this, 4 4 3 and 5, and finally in the sixth round it becomes like this, 4 4 4 4. So you can see it took total of 6 rounds to do this job transfer. Okay, so what I'm trying to say is, instead of thinking it like this, think this as a transfer between two parts of the array. Okay, so if I say this is one part of the array and this is another part of the array, finally this part should have 4 jobs and this part should have 4 into 3 12 jobs. Okay, so we have 10 jobs in this part and we require 12 jobs. Okay, so that means we need to gain 2 jobs here and we need to reduce 2 jobs here. That means at any given point of time 2 jobs will flow from this boundary to this boundary, so that means we need at least 2 rounds. Okay, If I think of other boundary, let's say 6 0, if I break about this boundary, finally I need 4 and 4, 8 jobs this side, and I also need 8 jobs this side. So currently I have 10, so it is having extra 2 jobs, and it is having a deficit of 2 jobs. So at any given time we would be transferring 2 jobs from this side to this side through this boundary. That would mean at least 2 rounds are needed, because that cannot be done in less than 2 rounds. Okay, so let's also think about this part of the array. Okay, and let's say this part of the array. Okay, so this part should have finally 4 jobs, this should have 12 jobs. That means it is having 6 jobs extra, and this is having a deficit of 6 jobs. That means 6 jobs must be transferred from this part of the array to this part. Okay, that would mean we need at least 6 rounds. Okay, so what should be the final answer? Okay, so at least 2 rounds, at least 6 rounds. So obviously it should be the maximum of this. So that would mean we need at least 6 rounds to transfer the load from one part of the array to other part. Okay, so I hope this case makes the explanation more clear. So this is what you actually need to do. Okay, so you have to find out the maximum transfers between two parts of the array, and these two parts of the array are from 1 to I and I plus 1 to n minus 1 for values of I starting from 1. Okay, so something like this you have to do. So if you want to see one more example, let's say this time there is like this. Let's say 0 6 10 and 0. Okay, let's try to do load balancing. So this time I'm expecting the number of rounds should be less, because we have the processors which are donors are at the center, and they may contribute on both sides. Okay, but let's see. Okay, so let's after first round it becomes like this: 1 5, and this gives this side. Okay, let's say 9 and 1. Then after another round, this gives 1 here, this gives 1 here, this gives 1 here. So it becomes 2 5 7 and 2. This is after first round, this is after second round. After third round, this gives 1 here, this gives 1 here, and this gives 1 here. So it becomes 3 5 5 and 3. Okay, then after one more round, it gives 1 here, it gives 1 here. It becomes 4 4 4 and 4. So it would require 4 rounds to do the transfer. Let's see if we can get the same through our approach. So if we just think about this as a boundary, 6 10 and 0, so we need 4 jobs in this part. Okay, finally, so we would need at least 4 rounds. Okay, okay, so if we think about this as a boundary, and we say, okay, here I should have 8 jobs, here I should have 8 jobs, so there should be a transfer of 2 jobs. Okay, so we need at least 2 rounds. And if we think of this as a boundary, 0 6 10 and 0, we need at least 4 rounds, because we need to transfer 4 jobs here. Okay, so at least 4 rounds. So the maximum of 4 2 and 4 is 4. That means 4 is the final answer, and that we have also verified. Same goes with this. If we just think of this as the boundary, 0 99 and 3, you would need 34 jobs in this. Okay, so that would mean at least 34 rounds is something that you would need. So this holds true for all cases, and I hope you got the logic. And in the next video we will discuss the implementation, but I suggest you to write the code yourself. Hey guys, in this video we will discuss the implementation of load balancing problem. Okay, so we have already seen how do we approach this problem, and now I will just show you the implementation that I'm going to do. Okay, so I'm given I've written some code. Okay, so I just read what is the value of n here, and then I will take input array, and if n is actually -1, then I stop. Okay, so that's given in the question that we have to do. So firstly we have to find the load that needs to be equally divided. For example, if there is like this 0, 6, 10 and 0, so the load that should be there in each part of the array is just sum of all the elements divided by 4, that is actually 4. Okay, so what we will do, we will take a variable load, and to that load we will keep on adding this thing, load plus equals to array of I. Okay, and here you can put a condition. If this is not a integer, then you can just stop. Okay, so what I'm going to do here is something like this. I can check if load is not a multiple of n. Okay, so if load mod n is not equal to 0, then I know it's not possible to divide the load. I do see out -1 and I stop. Okay, so let's continue. Otherwise the load that has to be equally divided is nothing but load upon n. Okay, so that's the load that should be there in each cell of the array, and then we will implement the greedy step for each partition starting from 0 to n-1. Okay, so we will create a partition at I equal to 0. That means we will have, okay, at this partition. Okay, so at this position I equals to 0, we will calculate what load should be there and what load is currently available. Okay, so something like that we will do. So what I will do, I will maintain a running difference. Okay, so let me explain you what I'm going to say. So I have made a variable called difference, that is 0. Suppose this is 0, 6, 10 and let's say this is 0. Okay, so here the difference would be between the load that is there, that should be there, that is 4, and minus the actual element. Okay, so actual element is 0, so 0 minus 4 is actually -4, and that means we need at least 4 transfers. Okay, so we will take the absolute value here if the load is negative, and this difference is -4. Okay, and let's go to this cell. This here also it should be 4. So what about this part of the array? Okay, how many transfers we should do in this part? So we actually know that this part of the array should contain 8 jobs, but it contains 6 jobs, so there should be a transfer of 2 jobs. Okay, but what I will do, I will maintain a running sum. Okay, like this. So firstly I know the sum is -4. That means here we have a deficiency of 4 jobs, and I go to the next location. Here I know I have 6 jobs, so actual jobs is 6, number of jobs expected is 4, so this is +2. So I do -4 plus 2, that gives me in this part there is a deficiency of -2 jobs. Okay, so there is a deficiency of 2 jobs, so that means I can say at least 2 transfers will happen. Okay, so at every okay, so I will maintain a running difference that will actually give me how many jobs should be transferred through the current partition. Okay, so that's what we are trying to do here. Okay, so difference is initially 0, as you can see, or we can make a variable here. Okay, so this is difference, and for this case I can say difference is 0 in the beginning, and I can say difference plus equals to array of I minus load. Okay, and then I can update my maximum load. Okay, so we have to take maximum to find the maximum load. So maximum load is max of whatever is the previous maximum and whatever is my current answer. Okay, so current answer will depend upon whether the value of difference is positive or negative. Let's say answer is max of difference and minus of difference. Whatever is maximum, that should be considered in the answer. Okay, and here I can say answer something like this. Okay, or you can just do, if difference is negative, then take it as a positive difference. That is one thing that you can also do. Okay, and then we do see out max load. Okay, so max is maintaining whatever is the maximum load we have seen till now. This is maximum of all possible transfers through different partitions of the array, and answer is nothing but how much disks we are transferring. So suppose this is -2, so we just make it as +2. Okay, so we see what is maximum 2, -2 or +2. So we take the positive quantity while computing the answer. Okay, and that's it. Okay, we have a undeclared identifier L. Okay, this should be removed. Okay, now let's try to run the code, and let's say we have 4 cells, 0, 6, 10, 0. So clearly we know the answer is 4 in this case. Suppose we have 6, again 4 cells, 10, 0, 0, 6. We should get a 6 in this case. We are getting it. Suppose we have 3 cells, 0, 99 and 3. So we are getting 34 in this case. So that means our implementation is correct, and this is how we could solve this problem, and I hope you got the solution. Hi everyone, so in this lecture we will be discussing the problem Defkin from Spodge. So let's go through the problem statement. So it's given there is a game called Defense of a Kingdom, in which you are given a rectangular grid of cells, and there are some towers in some cells of the grid like shown in the figure. The tower defends all the cells in the same row and the same column. Okay, so for example, if there is a tower at this position, then this entire row, the gray strip, is defended by the tower. Okay, and this column is also defended. That means it is a safe position. Okay, so you have to actually find out uh, number of cells in the largest rectangle that is not defended by the towers. Okay, this is what you need to output. So let's see what is a rectangle that is not defended by a tower. So it's actually uh, yeah, so okay, so let's see. So in this case, these white areas, okay, so these are the areas that are not defended by towers. So you want to find out the area of the largest rectangle that is not defended. For example, in this case, this area is 4 into 3, that is 12 units, and you can see the output is also 12 for this particular input. So let's understand the input format. So 1 denotes the number of test cases, then you have 15 cross 8, that is the grid size. Okay, and then you have 3, this is the number of towers, and then you are given the locations of these towers, x1, y1 and so on. Okay, so you have a tower at 3 comma 8, 11 comma 2 and 8 comma 6. So that this is given to you 3 comma 8, 11 comma 2 and 8 comma 6. Okay, so these locations of towers are given to us, and now we have to see how we can find out the largest rectangle. Okay, so let's talk about the solution. It's not very difficult, you can also come up with your own. So I suggest you pause this video before going ahead with the solution. Okay, so firstly, if you want to see what is the largest area, so area of the rectangle is defined as delta x into delta y. And if you want to find out the largest area, you need to maximize delta x and you also need to maximize delta y. So if you talk about undefended area, so any area that lies between two consecutive towers, this is actually an undefended area. Okay, this is a undefended area. This is also a undefended area. So you actually need to note what is the distance of first tower from the start. That strip is undefended, and then you have you note the distance between T2 and T1, and you also note the distance between T3 and T2, and you also note the distance between the ending of the grid and T3, the last tower. Okay, so the x coordinates given to us are 3, 11 and 8. So if we sort this list, we will get 3, 8 and 11, and these are the coordinates. This x coordinate is 3, this is 8 and this is 11. Okay, similar thing we will also do for y axis. So if I want to just find out this width, okay, so what I will do, I will subtract the starting coordinate. So starting coordinate is nothing but it's actually 0. So this width, so if you see the third strip is defended, so we will subtract 1. So this delta x will be 3 minus 0 minus 1, that is going to be actually 2. Okay, so this delta x will be 8 minus 3, but 8 is already defended, so we will subtract 1. So we'll say okay, 8 minus 3 minus 1, uh, that is actually 4. So you can see this delta x is actually 4. Okay, and then I will do 11 minus 8, that is actually 3 minus 1, 2. So this delta is actually 2. And finally, let's talk about this delta. Let's say this is 16 minus 11 minus 1. Okay, so it's like this is also 4. Okay, so 16 minus 12, this is also 4. So you can see this is also 4. So something of this sort we are doing. So it gives us a array of delta x, that is 2, 4, 2, 4. So this gives us what are the possible widths of rectangle. Now we also know that on every strip, on every delta x, we will have multiple delta y's. Okay, the first delta y is between tower T1 and this strip, so that is actually having a strip length of 0, this part. Then you have this is another delta y, this is another delta y, and this is another delta y. So these delta y's are also formed due to difference in the y coordinates of the two consecutive towers. Okay, so this delta y we can compute. So we know the coordinates are 8, 2 and 6. Let's sort these coordinates. So this becomes 2, 6 and 8. Okay, okay, so let's talk about this delta y. So this is nothing but 2 minus 1, 2 minus 0 minus 1. So this is 1 unit. Let's talk about this delta y. This is nothing but distance between the y coordinates of the T2 and T3. Okay, so this delta y is going to be 6 minus 2 minus 1, that is 3. Then this delta y is going to be 8 minus 6 minus 1, that is 1. And finally we will have a delta that is 9 minus 8 minus 1, that is 0. Okay, so now you know what is a possible delta y and what is a possible delta x. And if you want to maximize this product delta x into delta y, you will pick the largest delta x and you will also pick the largest delta y, and both of them can be combined independently. Okay, if you see, if you talk about this delta y, this can be combined with this delta x. Okay, or it can be combined with this delta x, or it can be combined with this delta x, or it can be combined with this delta x as well. Okay, so any delta y can be combined with any delta x, but if we want to maximize the product, so we will pick the largest delta y, that is 3, and we will combine with the largest delta x, that is 4. So this will give us the largest undefended rectangle, that is 12. Okay, so this is about how you can approach this solution, and that's all for this video. Thanks a lot. Hi everyone, so in this video we will discuss the implementation of the problem defkin. So I'm reading test cases. So first step is to take input the grid size and the number of towers, and after that what I will do is I will scan the coordinates of n towers. Okay, so from int I equals to 0, I less than n, I plus plus, I will store the coordinates of the ith tower in the array x and y. So after that what we need to do, we need to do sorting so that we know what towers are consecutive, which tower is the next tower of the ith tower. Okay, so sort the x coordinates, so sort x plus n, and similarly we will sort the y coordinates, y plus n. So after doing sorting, what we need to do, we need to find out delta x and delta y, so that we are able to find out the maximum area. Okay, so what we can say, okay, so firstly we will calculate delta x between two consecutive towers, and then we will handle the corner cases. Okay, so I can say the initial delta x, that I can say it's nothing but this is equal to, let's say, x of 0, and I can say this is, and initial delta y, this is equal to y of 0. Okay, so if you see carefully here, the, let's say, after sorting, the initial x coordinate is 3 and y coordinate is 2, so this dx should be equal to x of 0 minus 1. Okay, so let me update it, because this coordinate is 3 and for this delta x is 2, so I just have to put it like this, minus 1, and initial dy, that is also minus 1. Okay, so this dy is minus 1 because this coordinate is 2, and for all others I will find out the difference between the consecutive towers. Okay, for int I equals to 1, I less than n, I plus plus. So I have considered the contribution of the zeroth tower. I'm starting from the first tower. So what I'm trying to do here is I'm trying to update my dx as maximum of old dx and the new dx. So the new dx will be my point xi minus my previous point, that is x of I minus 1, and I will subtract 1 here. Okay, and dy will be max of dy yi minus y of I minus 1 minus 1. So this will give me the maximum value of dx and dy. And finally we have to consider the corner case when the grid is ending. Okay, so this case, from the end of the grid to the last tower, so the last tower is in the n minus 1th index. Okay, so last tower to grid end, so that is nothing but dx will be maximum of dx, and in this case when we are computing this, we don't have to subtract minus 1. Okay, because the last index is 15, and if you do 15 minus 11 you will get 4, or you can say, yeah, that's what you can do. So you can say this is width minus x of n minus 1 and dy is maximum of dy and height minus y of n minus 1. Okay, so this completes our logic to find dx and dy. And finally, if you want to find out the area, that is C out dx into dy and L. Okay, so okay, so yeah, let's remove this. Yeah, now it's looking fine, and let's try to run the code from command line. Okay, so let me give one test case, and let's say the numbers are like this. Okay, so we are getting the answer as 12, which means our implementation of this is correct. Okay, so that's all for this video, and thanks a lot. Hi everyone, so in this video we will discuss this problem, chopsticks from Code Chef. Okay, so let's go through the problem statement. So it says you are given some number of chopsticks, and to eat you need to pair two chopsticks, and each chopstick has a different length. Okay, so let's say there is a chopstick 5, 3, 6, 8, 1, something like this. So there are chopsticks of different length, and you want to eat, and you to eat you need two chopsticks, and it says two chopsticks can be paired as long as the difference in their length is at most d. Okay, for example, d is 2, then you can pair 5 and 3. You can also pair 6 and 8, and you have to find out what is the maximum number of pairs you can form for the chopsticks. Okay, for example, in this case you had 5 chopsticks, but you can form only 2 pairs, or you can say 4 chopsticks can be paired together. Okay, so that's what you need to do. Okay, so now you have to think up of a solution in which, and you can see the constraints also. N is of the order 10 by 5, which means we can do something of n log n sort, n log n type. Okay, we cannot do n square. Okay, we cannot try each chopstick with every other stick. Okay, so this is for d is 10 per 9, so maybe we can just store everything in long int. Okay, and l of I, that's also 10 per 9, so int is also fine. We can store it in int as well. Okay, now in this example you're given chopsticks like this 1, 3, 3, 9 and 4. So you want to find out the pairs, and it's given d is 2. So clearly we have to come up with an algorithm that does this work. So what you can do is, uh, firstly, if you pick this particular chopstick, you know you want to pair this chopstick. Okay, so what would be the best option to pair? So should I pair it with 9, or should I pair it with 3, or should I pair it with 4? Obviously I should pair it with the nearest chopstick. Okay, with the nearest means the chopstick which has the very similar height than it. Pair it with the nearest chopstick. So that means I should know that for 1 the nearest chopstick is 3, and for 3 the nearest chopstick is 4, and then we have 9. So that means we should first sort the chopsticks according to the length. Okay, according to the length. After that you can see if you can pair L1 with L2. If L1 and L2, that is, let's say this array is L. Okay, if L1 and L2 can be paired, that means you should pair them. Okay, so if 1 and 3 can be paired, you should pair them. Okay, But for example, if day is 3, okay, or let's say day is 5, then you cannot pair 1 and 3, and that would mean 1 is useless. Okay, so if L1 and L2 can be paired, use them and remove them from the list. Okay, remove them from the list. Okay. So how do you remove them? You can keep a pointer I, and if you're able to pair these two, you take I equal to I plus 2. You come to this position. Okay, but if L1 and L2 cannot be paired, if you can't pair L1 and L2, then you remove L1. Maybe 1 is useless, something of this kind. For example, you have chopstick 1, 4, 6, then let's say 7, 10, 12. So if you cannot pair, let's say D is again 2. So now you cannot pair 1 and 4, so you remove L1. So you take I to the next position, I equal to I plus 1. So you try again. Can you pair 4 and 6? Yes, we can pair. So you form one pair. Go to the next position, I equal to I plus 2. Okay. Can you pair 7 and 10? No, we cannot pair. Skip this one. Go to the next position, I equal to I plus 1. Because if you are not able to pair 7 with a chopstick 10, it cannot be paired with any other chopstick 12, 15, 13, because this distance is going to increase further. Okay, so if it cannot be paired with the nearest chopstick, it cannot be paired with any chopstick that is having a greater length. So obviously this is a greedy approach. Okay, so this is a greedy thinking. If you cannot pair a chopstick with the nearest chopstick, then you cannot pair a chopstick with the chopstick having a higher length. Okay, then you remove the current chopstick, you remove L1 and go to the next position by saying I equal to I plus 1, and here you do I equal to I plus 2, and you keep on repeating these steps until you reach end of the list or the list is not empty. So that's it. That's the very simple algorithm, and I hope you would be able to code it and submit it. Okay, so that's all for this video. Thanks a lot, guys. Hi everyone, so in this lecture we are going to discuss a very interesting problem, that is expedition from Spotch, and it's a slightly harder problem as compared to other problems we have done till now. So the problem statement is like this. Okay, so there is a group of cows who are grabbed in a truck and they are stuck in a jungle and they want to reach a town. Okay, so something like this. There are cows in the truck and they want to reach a town which is some kilometers away from the current location where the truck is. Okay, so we want to go from the source to the destination, and the truck leaks 1 unit of fuel for every distance it travels. Okay, so if a truck goes 5 kilometers, it the fuel reduces by a factor of 5, and to repair the truck the cows need to drive to the nearest town. Okay, so the goal is to reach this particular town, and there are n number of fuel stops where cows can stop to acquire the additional fuel. Okay, so the truck is having cows, and there are some number of fuel stops. This is a fuel station F1, this is fuel station F2, F3, F4. Okay, so there are fuel stations from which you can acquire additional fuel, and maximum fuel available is 100 units at each stop. The jungle is a dangerous place for humans and for cows. Therefore, cows want to make minimum number of stops for the fuel on the way to the town. Okay, so the cows want to stop at minimum number of fuel stops, and good thing is the capacity of the fuel tank is so large that it can acquire any amount of fuel. Okay, so you can put infinite fuel in it. Okay, so there is no limit how much fuel you can have inside the truck, and initially the current is truck is L units away, so this initial distance is L units, and it's given in the sample input. This is 25 units away, and it has P units of fuel. So the initially capacity of the initial fuel in the truck is P units, and P is given as 10. Okay. So we have to find out what is the minimum number of stops that is needed to reach the town, or if the cows cannot reach the town at all. Okay. So if it is impossible to reach the town with the given constraints. Okay. So this is what is given to us. So we are given in the sample input one test case. 4 is the number of fuel stops, and followed by 4 lines, and each line denotes the distance of the fuel station from the town. Okay, so it's given there is a fuel stop at a distance 4 from the town. So distance is with respect to the town, that's given in the question. Okay, so it means this is the fuel stop, it is at 4 distance. So that means this fuel stop is actually at a distance 25 units or 21 units from the truck. Okay, because total length is 25 and 4 from the right would mean 21 from the left. Similarly, another fuel stop is there, that is 11 units away. So that would mean it is at actually at uh, okay, there is another fuel stop which is 5 units away. So there is a fuel stop at 20. There is a fuel stop 11 units away. So that would mean 25 minus 11. That is at a distance of 14. And there is a fuel stop which is 15 units away from the town. That would mean there is a fuel stop at 10 units. Okay. So we actually have 21, 20, 14 and 10. So 10, 14, 20 and 21. So these are the x coordinates of the fuel stops from the truck. Okay, so these are the distances of the fuel stops from the truck, and we are also given the fueling capacity of each station, how much fuel is available at each station. So here you have 4 units. Okay, so this is 4 units, this is 2 units, this is 5 units, and here you have 10 units. So these are the fueling capacities of these stations, which means they can give at most this much quantity of the fuel to the truck. Okay, so these fuel stops can supply 4 to 5 and 10. So 4 to 5 and 10 respectively. Okay, so now you have to find out if we can reach the town or not. Okay, so let's try to think. So let us suppose you initially have 10 units. So clearly using 10 units you can reach this fuel stop, and at this location the truck will have a fuel capacity of 0, and you will add 10 units of fuel from this stop. So you have used one stop, and using these 10 units, although you can go till this particular stop, but okay, one option is you have 10 units, you go till this stop, again you will have 0 units of fuel, you get 2 units, that would make you reach 21, and at this point you will have 1 unit of fuel because you have traveled 1 kilometer, and you add 4 more units, so that would make you reach 25. So in this case you are using 3 stations. Okay, but a better way would be you can also do it using 2 stations. Okay, so let's see how we can do it using 2 stations. Okay, so you come to this stop. Okay, and from here you start driving to the next, and let's say you stop at 14. So at 14, how much fuel a truck will have? So you had 10 and you traveled 4 units. So at this point the capacity was 10, and at this point the capacity would be 10 minus 4, that is 6, and you add, let's say 5 units of fuel. Okay, that would mean you now have 11 units of fuel, and from 14, by using 11 units of fuel you can reach 25. That would mean you just stopped at 2 fuel stops and you are able to reach the town. Okay, so the final answer is you can reach the town using minimum 2 stops. Okay, so 2 is the correct answer. Okay, So now we have to think uh, how to approach this problem. Okay, so what we can do, let us think of the solution. Okay, so one thing that is coming to our mind is we should refuel at stations which have a higher capacity. Okay, if we want to minimize the total number of stops, so we should refuel at stations having large fuel, okay, large value of F. So that gives us a hint we need some kind of sorting. Okay, so my first question is, if we directly sort the fuel stations according to the fuel capacity, will it work? The answer is obviously no, because suppose you are standing at this point and you have 10 units of fuel, and there is a fuel station 30 kilometer away and that is offering 100 liters, and there is a fuel station at, let's say, 10 kilometer away which is offering 5 liters. Okay, so obviously you would still need to refuel at this station to go further. Okay, you cannot directly pick this because this is not directly reachable, not directly reachable. Okay, so that is one thing. Okay, so what you need to do, we will do sorting for fuel stations up to which we can reach with the current capacity. We can reach with the current capacity. Okay, so what I will do, I will keep on moving in the forward direction, and I will keep a note of fuel stations that are available. Keep a note of fuel stations that are available. Okay, and if at any point I think I have a shortage of fuel, I will pick the largest station that is available. I will use it and remove it. Okay, pick the largest that is available, and still if I have shortage, I will pick the next largest. Okay, I will pick the next largest, and so on, and I will keep moving in the forward direction. And while moving forward, if I encounter there is a fuel station offering a capacity F, I will add it. I will keep a note. Okay, so how do we keep a note, how do we keep a track? Okay, so for that we will use the priority queue data structure. Why we are using priority queue? Because at any given point it allows you to get an excess of uh, what is the largest value. For example, we must have solved some problems on you must have seen some problems like largest in a stream of k largest elements in a stream of in a running stream. Okay, k largest numbers in a running stream. So these fuel stops are like a running stream, because uh, as you're going forward, 8 3 6 10 4. Okay, so as you're moving forward, you keep a track of what fuel stations you have encountered. Suppose you reach up to this point, so up to this point, I have encountered 10 8 6 and 3. So I need to store. Okay, if I want to refuel at this point, which fuel station will I choose? Obviously I will choose the station 10, or let's say there is a station 40. I will not choose 40 because I have not reached till 40, or I cannot reach till 40. Okay, so we will keep a track of what fuel stations we have seen till now, and we will refuel only at those stations which offer a higher capacity. And if needed, once we have consumed a particular station, we can also say, okay, this station is not available because we have already used it, and we will pick the largest from the remaining list of numbers. Okay, so something like that we are going to do. So if I just show you an example here, so what we will do for this, we will make a priority queue, and suppose you start moving from this location and you reach this location, and at this location you see there is a fuel stop which is offering 10 units, so add it to the priority queue. And at this point the truck needs more fuel to go further, so you empty this from the priority queue, you refuel the truck, and truck again gets a 10-liter capacity. Okay, and you keep moving forward, and when you reach this particular point, you see, okay, there is a fuel station which is offering 5 liters, and the truck now has a capacity of 6 liters. So from 14 you can go to this fuel station also, because you have a capacity 6. So you see there is a fuel station which is offering 2 units, so you add it to the priority queue. And now you see, uh, when you reach this particular station, you see you need actually more fuel. So what you will do, you will pop this from the priority queue and refuel your truck, and your truck will now have a capacity of 5 units. Okay, and from this you go to this place, and you see there is a fuel station which is offering 4 units, so you add it to the priority queue. And at this point, your truck will have a capacity of 4 units, and you know that to reach the town you just need 4 units of fuel, so you do not refuel. Okay, so you go and reach the town. Okay, so that means from the priority queue you have used 2 fuel stations, and 2 fuel stations are still there which we have not used. And obviously we use the fuel station which were having a larger value. Okay, and since it is a priority queue, 4 will come here and 2 will come here due to the heapify operation. Okay, so something like this. So you can just solve this problem in n log n time, because of the priority queue. Okay, so this is about the logic of this problem, and in the next video we will see the implementation. Hi everyone, so in this video we will discuss the solution to the problem expedition from Spotch, and I will write the code for it. Okay, so let's see how we can implement this problem. Okay, so firstly I'm going to define few things, few variables. I will explain what all these variables are. Okay, so firstly we need to input the number of test cases, and for each test case we have to do some work. Okay, so firstly I will make a vector to store the fuel stations and their capacities. So it will be a vector of int, let's call it as v, and we will also need a priority queue to store the capacity of the fueling station. Okay, that we discussed, so that is there. And after that we can scan how many stops we have, that is the number of stops. And then for each stop we have to read what is the location of the fuel station and the capacity it is offering. Okay, I less than n, I plus plus. So we will read two things, the distance and the fuel. So this d and f is that. So we can say c in d and c in f, and we can say v dot pushback make pair d comma f. So that takes the input, and from here we can start our logic. Okay, so firstly what we need to do, we need to sort the cities according to their location. So let's sort the cities according to their location. Okay, so we'll use the sort function, v dot begin and v dot end, and we need to make a custom compare function as well. Okay, so let's make this bool compare function, and I can say I'm going to compare two pairs. So pair int uh, p1, pair int p2, and I can say return p1 dot first greater than p2 dot first. So I'm comparing two fuel stations based upon their distance from the town. The one with the smaller distance from the town will be the bigger one. Okay, because that is away from the city, so that's why I'm using a sign greater than. And we also need to scan two more things that were there in the input, we are yet to scan. So we need to scan the value of L and P, so the initial distance and the initial capacity of the truck. So let's call it as capital D and capital F. So I will read it. Okay, so see, in capital D and capital F, and also what I need to do is I need to update the distance. Okay, so let's update the distance of the fuel station from the truck. Okay, from the truck. So I'm going to iterate over the vector. So initially I have created this vector like this, 20, 20, 14 and 10. Actually I want to create this. Okay, so we have 4, 5, 11 and 15 from the town, that is sorted in the reverse order, and we will subtract every value from 25 so that we know the distance from the truck. So for int I equals to 0, I less than n, I plus plus, I can say v of I dot first equals to d minus v of I dot first. So that updates the distance of the fuel station from the truck, and it is also sorted because for the town we have done the reverse sorting. Okay, now we will start with the actual logic. Okay, so what we will do, we will have a variable called previous that denotes the previous city we have visited. So let's say previously we are at 0, we are yet to start. Okay, so let me just say previous is 0, and let me take a variable x that denotes the current coordinate or the current city where we are at. Okay, so this is my current city. So what I need to do, I need to visit n number of cities. So I can say while x is less than n. Okay, so what we are going to do, we are going to see if we have enough fuel to go to the next city. Okay, so if we have enough fuel to, so capital F denotes the current capacity of the truck, current fuel in the truck to go to next city. So I can say if F is greater than equal to uh, whatever is the next city, that is v of x dot first, that is the location of the first city or the next city, minus my previous location, that is 0. If I have this much of fuel, so I will go to this location and I will reduce the capacity of the truck by this amount. So I can say F equal to F minus this particular value, v of x dot first minus previous. Okay, so this reduces the capacity of the truck, and since we reached a next city or the next fueling stop, to our priority queue we will add that fuel stop. So I can say priority queue dot push v of x dot second. So that will add that particular fueling station to my priority queue, and now my previous will also get updated. So previous will be v of x dot first. So we have actually reached the first city and we have updated our, okay, so what we have done is we reached this particular city, that is my first fueling stop, and to reach it I needed 10 units of fuel. So the capacity of the truck that was 10, that is now reduced to 0, and to my priority queue I have added this fueling stop which offers, let's say, 5 units of fuel. So priority queue now contains number 5, and I now say okay, now we are at standing at this location, so this is my previous. Okay, something like this. So what we need to do next is, okay, let's also write the else case. If this is not possible, if we cannot reach the next city from the current fueling capacity, what we can do, we can check if you have some fueling stations visited in the priority queue. Okay, so you have encountered some fueling stations on your way. Now there can be two cases, you might not have encountered any fueling stations. So if priority queue is empty, that means no fueling stations were present on your way. So what you will do, you will say okay, this is actually not possible, So maybe we will keep a boolean variable, let's say flag, that is, let's call it as 0. Okay, int flag equals to 0, and answer will store the number of fueling stations we have visited. Okay, so we can say, okay, flag equals to 1. That means this is not possible, and we'll break this loop at this point. Okay, otherwise, what we can do otherwise? Okay, otherwise we can refuel the truck with fueling station with higher capacity. Okay, something like that. So I can say, okay, remove a fueling station from the priority queue and add the fuel to the truck. So f plus equals to pq dot top, and since we can use a fuel station only once, we will remove that fuel station from priority queue. Okay, so we can say, okay, pq dot pop, that removes the fuel station from the priority queue, and since you have used a fueling station, I can say answer equal to answer plus 1 and continue. So continue means continue exploring, let's go to the next city. So this will resume this while loop. Okay, something like that. Okay, so we have done two cases. If we can go to the next city with the current capacity, we will go. If we are shortage of capacity, we will try to remove a fueling station from the priority queue, and we will try to visit the next city. Okay, so at this point, it is also possible that we may need. Okay, so let me just make this statement more clear. So this continues for suppose you are standing at a particular location, and you had encountered three fuel stops, one with the capacity 6, one with the capacity 2, and one with the capacity 8. And at this point you realize that to go further you need at least 14 units of fuel. Okay, so at this point you have in your priority queue 8, 6, and 3. So maybe this is your current location, and this is the next location where you want to go. So you see, okay, this is my previous and this is my x. So if you say, okay, I cannot go up to this point even after, let's say, fuel at this point is 0. So you remove a fueling station, that is 8, and you add it to the fuel capacity, so it becomes 0 plus 8. But still you observe that I cannot, using continue, go come to this point, and you say this if is still not true. I want to travel 14 units, but still I have 8 units of fuel. So you again come to the else block and you pop another fueling station that you have encountered on your way, and you refuel it. So that is why this continue is important to put at this point. But suppose if you are able to reach that particular point and you come out of this if block, so you will end up at this point. So that means you have encountered you are able to visit a next city, and that will increment the value of x. Okay, so while x is less than n, that means you and if you come out of this while loop, you have actually traveled through n fuel stations. Okay, so finally what is left is you have to reach the town from the last fuel station. So that thing is left. Okay, so if you have 4 fuel stations and now you are standing at the final fuel station, and from this you have to go to the town, and at the town you don't get any fuel. Okay, so this case you have to handle separately. Okay, so at town what you can do is maybe some of the fuel stations you have used, and at this point you can check if you have enough fuel to reach the town, then it's great. If you don't have enough fuel, you try to recharge the truck from the remaining fuel stations which you have not used. So that is what we are going to do. Okay, so one thing we can do here is, if flag is 1, that means if the solution is not possible, we can just do cout -1 and endl without checking any further. Okay, so we say okay, continue. Otherwise we can check if we can reach the town. So the distance of the town from the last fueling station is uh, this distance, d minus v of last filling station is n minus 1 dot first. So if you have enough fuel to cover the last distance, then you can say cout whatever is the answer you have, how many stops you have visited, that's it, and continue. Otherwise you have to check. What you have to check? If the priority queue has enough fuel to make you reach the town. So while I can put a while loop, while f is less than d, while your available fuel is less than the distance traveled, you continue to recharge your truck. Okay, so if priority queue is empty, then you cannot reach. Okay, and you have fuel which is less than d and priority queue is empty, then definitely you cannot reach. So you can say flag equals to 1 and break. Otherwise you can say okay, recharge my priority queue. So f plus equals to pq dot top, and you remove that fueling station from the queue, and you say answer equal to answer plus 1, because you are using one more fueling station at this point. Okay, and that's it. So this while loop will make sure that if you are able to, if you have enough fuel to reach d, you will be able to reach, otherwise you won't be able to reach. And finally again you can make a check if flag is 1. Okay, you can say okay, uh, yeah, for this. Okay, so if flag is 1, you can say cout -1 and l and continue. Otherwise you can just say okay, this is my answer, cout answer and l, that's it. And that's complete our code. Okay, so let's try to run this code. Okay, we have seen t. Okay, this should be t. Okay, x is not defined, so we can define x maybe like this. Okay, looks fine. So let me just give some input and output. Okay, 144. Let me copy it from Spotch. Okay, so we are getting the answer as 2, which means our solution is correct. And if you want to have a brief recap of what we have done till now is, so we have mainly two components in the code. One component is to visit all the fuel stations, and that has two cases. If you have enough fuel, you directly go to the next stop, and if you don't have enough fuel, you continue to recharge the fuel from the priority queue in this loop, and x plus plus increments the cities you have visited. And the second component is about if you want to travel from the last fueling station to the town, then you have this distance that needs to be covered, distance minus the distance of last fueling station, and you want to travel this much distance. And if you don't have enough fuel, you keep on recharging the fuel from the priority queue, and if at any point priority queue becomes empty, that means it's not possible to reach the last station, and then you do cout -1 and you do handle. Okay, so this is how we have broken down our problem and solved it with the help of priority queue. And this problem was little challenging than other problems, but I hope you are able to get the solution now. And thanks a lot for watching.
So the problem is 564A code forces, and it's a div 1A problem. So actually it's quite a good problem based on greedy algorithms. So however, it is somewhat better problem as compared to other div 1A problems because it's a bit difficult to think of it, but once you have the solution, like an approach, then it's quite easy to code. So yeah, so let's start the question. The question is something named Now and cards. I don't know whether I'm pronouncing the name correct. So we have two piles actually. One is a pile and one is a set of cards that a girl, let's name the girl Alice, has, and this is a pile. Now there are actually 2 into n total cards in this whole deck, out of which n cards are numbered from 1 to n, and the remaining n cards are empty. We can consider as a 0 being written on them. So now the task is that we have to arrange this pile into an increasing order, like we have to reach this configuration. Initially it can be something like this. Yeah, so the pile also consists of n cards, and the set of cards that Alice has is also n. So we are given an array of size n, which is A, and an array of size n, which is B. Yeah, and we are also assured that every element is like from 1 to n is present exactly once, either in array A or in array B. Yeah, and we have to reach this configuration. Now the operation that is allowed to us, the operation that is allowed is that we can pick one element from the top of the pile and move it over here, and at the same time pick one element from here and move it to the bottom of the pile. It can be any element, not this. We cannot shift this element from top to bottom. We need to first move it over here and then move some other element towards the bottom of the stack or the pile. And then we have to reach this configuration somehow. So even if the question isn't clear by what I said, then you can read the question. Now let's jump on to how can we think of a solution to this problem. See, thinking of a solution in competitive programming should be, you should have an ideal approach. Like you should consider some cases and think that how it's working. So what I thought of it in the first go is that I have n cards over here and n cards over here. Like what is the first thing that came into my mind was, what is the maximum moves in which I can sort? In which I can sort the pile. And if you ask this question to yourself, then you are mostly done with the question. So the maximum moves can be no more than 2 into n. You can think of it. How? So it's very easy to analyze. So what happens is that your pile may contain some random numbers in some uh, distorted order, and you need what you need to do is that for every zero over here, there will be surely a one present over there. Oh, a number which is non-zero present over there. So you just need to put all the elements which are non-zero from this pile to here, and from here, you, since there is no order, you can then swap every zero with a non-zero number. So actually, this let's consider a case wherein I can get the maximum answer. You can analyze how I thought of this, but it's very easy to think. 4, 3, 1, 2, let's assume anything. This may not be the optimal solution for this, but the maximum solution for this can be uh, this only. Like the maximum moves can be, if I bring the 4 out and then put the 0 in over here, 3, 1, 2, 0, then I bring the 3 out as well, and I should change the order instead, else the answer would be 1 less. So yeah, so 3, 2, 1. Now I have pulled out 3, and now the stack is like this. Next I have pulled out 3, 2, 0, and the stack now looks like, and finally 4, 3, 2, 1, and the stack looks like this. Now you can see that once I have all of these elements, non-zero elements over here, then it's very easy to pick up one element from the top of the pile into this, and then pick the smallest element from here and move it over here. So after this, I know that I require 4 steps only, and to reach from anywhere to this configuration also, I require 4 steps at max. So actually I require 8 steps, and I can solve this problem in 8 steps. So for any given n, I can solve this in 2n. That's the beauty. So once you are done with this thing, you know an upper limit. Now, you know an upper limit, and you know that, so whenever there's a thing where you can find in an upper limit and you think it's a greedy solution to it, you can always apply a binary search method. Or in most of the cases, you can go with binary search in that. So now I know an upper bound to solve the problem, which is 2 into n. And what can be the lower bound? The lower bound can be 0. I don't require any moves to solve the problem. So my lower bound is 0 and my upper bound is 2 into n. After this, one more thing which is required to apply binary search is that it should be an increasing function. Never apply binary search without realizing this condition. So let's assume that I can achieve this solution by applying some moves, let's say x. Then can I achieve the solution with moves x plus 1 as well? Obviously yes. So it's basically very easy, because I'll just start putting into the pile one step later. So after swapping once, so that will make things very easier. So once you have realized this, you know that it is an increasing function. So like I'll consider the case wherein if I'm not able to solve the problem, I'll mark it as 0. But if I'm able to solve the problem, I'll mark it as 1. So once I start getting ones, it will always be one beyond that. Because if I can solve it in less number of moves, then I can surely solve it in more number of moves. So I need to just find the location of this first one in an array from 0 to 2n. As simple as that. So this is how I'll come to the binary search solution for this problem. However, there can be one more case which needs to be taken into account before starting to code for this. Yeah, and that case is very easy to formulate in your mind. So the case goes like, if my array is something like this and my pile looks something like this. Is actually the first test case of the question as far as I remember. So yeah, so in this case what happens is that I don't need to bring out people from the start to do anything over here. So the point is, I can just bring in the 2 over here, swap it for 3, and now my pile looks like 0, 1, 2. And after that 0, 3. In my opinion, I coded specifically for uh, an ending sequence starting from 1. This may be 1, 2 at the end. So we can analyze over this as well, that if this is possible. But you can skip this part as well. So now once you have started this, so this is a very simple binary search approach. You don't even need to code specifically for this case. So the point is, you just need to run from 0 to 2 into n, and what your evaluation function in binary search would return, it would return a 0 and 1. It would return a 0 whenever it isn't possible, and it would return a 1 whenever it's possible to solve the question. Whenever it's possible to move, perform these many moves and sort the pile. So the greedy strategy would be very easy over here. I'll just pick a 2. And so the greedy strategy actually, the binary search, if I'll assume that I'll have some x moves. So I coded for this part specifically because in this case I don't need to start all over again, because but in one case you need to start all over again, and this can be something like, if 1 is already at the top of the pile and you have 0, 2, 0, then you need to bring the 1 out of the stack, 0, 1, 0 and 0, 3, 1, sorry, 0, 3, 2, anything like this. And so this would require actually more than 3 moves. So the way we code for this is that we handle the case which is starting from 1 at the end of like, if the pile already has 1, 2, 3 at the end and some numbers over here, then we check if we can insert these over here. Or the second case would be that we bring out some level of elements from this from the top of the stack, and then put them one by one inside the stack or the pile. So like, we'll start so the binary search would actually be running from 0 to n over on this case, wherein I don't have an ending sequence like this. If I don't have an ending sequence like this, I need to pull out something from the stack and then start it. Or maybe pulling out nothing also works from the stack. So once I have done this, now the solution to this problem is very simple. For each binary search, I'll be working as follows. Yeah. So now the problem is reduced to 0 to n. As the first step would be to bring out some x elements from out of the stack and then start putting in. So the thing which I observed was that, let's assume I have pulled out some x elements from the stack, which can be 0 as well. I'll always pull out non-zero elements, and the 0 elements could always be swapped for a 0. So that's not an issue. Now, if I start putting just after I pick the x elements from the stack, so then how will I handle the situation? It's very easy. Once I pick out x elements from the stack and then start putting inside it, then I just need to define a starting position wherein I start putting into the pile. So where 1 should be present into the pile when I start putting in. Then 2 should be present on the at least x plus 1th location. Anywhere before this, like 2 can be present over here or here, but if not here, 2 should be present over here before I start putting into this pile. If I start putting into this pile after x elements have come already. Because if 2 is at some lower position, let's assume, then actually when I'll be searching for the x plus 1th element, 2 wouldn't actually be there. And so I have to insert some other number which would surely not give me the optimal answer. And this is the crux of the problem which you have to realize over here. So the 2 should be present over here at max. If it's present somewhere in here, then there's no need. But if 2 should be present either in this or at max at the x plus 1th position. 3 should be present at the x plus 2th position at max or anywhere before this. So this, because whenever we are putting into the pile, we should have that element available. And this is the whole condition for our binary search evaluation function. So we can only evaluate for a certain number of moves if we know that. So we can very easily now search for all the x which range from 0 to n and return a 0 or 1 as we get the answer. And once we get the answer for this, we know that after putting out x elements from the stack, if we start from that particular point, then we require n steps extra to insert all of these elements one by one, because then we'll be starting to put into a pile means we are putting first one into the pile. So obviously 1 should be available, and then x plus 1 is, until the x plus 1 is positioned, the 2 should be available, and so on. So this is how the binary search function would work, and yeah, now coding it would be very easy. Thank you.
Hi everyone, in this video we are going to see about the Huffman encoder. So basically Huffman encoder is an application which is being used to compress the data and store it in a file, and later on to retrieve that data from the file, encoded data, then decode it and then read it. So basically Huffman encoder is being used to store the data by using less number of bits or bytes in the hard disk. So it is used for space optimization. So let's see how the Huffman encoder works. So for an example, let's say we have a string A, B, B, C, D, D, A. So let's say we have the string. So as we know, this is a string, so it is made up of characters and each character will be taking 2 bytes. So in total, there are 3, 6 and 7 characters in this string. So this will take total space equals to 14 bytes. 7 into 2, 14 bytes, which is further equivalent to 14 into 8. So we know that 1 byte is of 8 bits. So 14 into 8, it is 112 bits on disk. So storing this string of 7 characters will take 112 bits on a hard disk. Now, what we want to do is we want to store it by using less number of space or less number of bits. For this, we use Huffman encoder, and let's see now how the Huffman encoder works. So, in Huffman encoder, what we will do is we will create two hash maps. So we will have two hash maps. So this one hash map will be our known as encoder, which is being used to encode the data, and another one will be a decoder, which will be used to decode the data. So this is my encoder. So let's say in my encoder, what I will store is this will be a hash map, and so its key will be the character. The characters of my string which are occurring inside my string, the characters which are occurring inside my string. So it will have a key of type character and its value will be a string. That is whatever we will be encoding for this particular character. So our encoder will look something like this: A, B and C, D, because there are only 4 unique characters which are occurring inside our string. So for each character we will have a unique value A, B, C, D. And similarly, on the decoder side, what we will have is we will have string as its key and character as its value. So these strings now will be stored in the decoder as a key, and the value will be the corresponding characters A, B, C, D. So this will be the basic fundamental of Huffman encoder. Now what we will see is we will see how we will build this thing, how the Huffman encoder works practically. So we will be using encoder and decoder. So let's see this thing. Now let's say what I will do is the first steps which will be involved in Huffman encoding will be, the first thing is pass the data, pass the string which will be known as the feeder. First step. So we will be the passing the string. Let's say a string in this case is okay. Let's say we are not taking a smaller string, we will just do something else. So we will just pass the string whichever we want to encode. So now the first step will be, after passing the string, what we need to do is make the frequency map of the characters. So we will be making a frequency map of the characters. So let's say we know how to make a frequency map. We have done it earlier also, and you know now the basis of hash maps. So we will be making a frequency map of characters. So the frequency map of characters, let's say, looks like there was a string in which A was occurring around 60 times, B was occurring around 30 times, C was occurring around 8 times, and D was occurring around 2 times. So this is my frequency map of the string which I have got. So my first step is always to create a frequency map. So I have made this frequency map now. Now the second step will be for each key in frequency map, what I need to do is I just need to create a node. So for every character I will be creating a node and insert that node in a priority queue or a heap. So both are same. So we will be inserting it into a heap, and this heap will be a min heap. So what we will be doing is we will be inserting this thing in a priority queue and or a min heap. So now this node will have four things with itself. One will be the data of type character, one will be the cost. So cost will denote nothing but just the frequency of this character. So A, its frequency 60, so its data will be A for this key and its cost will be 60. And then we will have the reference to the other nodes, which is left and node right. So this thing is almost similar to like your tree node. So it is pointing towards left another node and other right node. So these are the four things which every node will have. Okay. Now let's say I have built a heap with this thing, filled all the keys. So now my heap will contain four nodes. So let's say this is the node 1. So this node 1 will have four things available. Its left is null, initially right will be null, and its data is A, and its cost is 60. So these are the four things for this node A. Then I will also be having a node for B. So this was A, this is B. For this it will be, its data will be B, its cost will be 30, its left will be null and its right will be null. initially. Now another node which I will also be having is C, its cost, its left null, its right null for C. And then I will be having D, data as D, cost as 2, its left null, its right null. So this is how I will be having these four things in my heap. So we are not here discussing the order how they will be formed in a heap, because we know that we are creating a min heap. So in the min heap, the D will be at top, C, B and A will be at the bottommost level. So we are not here seeing the specific order, but we know that it is a min heap. So D will be at its top and C will be the second smallest value. So this heap will be a min heap which will store the information of all the nodes. So all the nodes are lying inside this heap. Now let's see what is the third step. So in the third step, what we need to do is, for each, we need to loop through this heap. So now what we need to do is, while looping, we will remove the two elements from heap and we will combine them. And we will do this step again and again until the size of heap remaining is just 1. So now let's see what we are doing here. So this is our heap. So we will loop inside this heap until its size remains just 1. So for first of all, we will remove the two elements from the heap. So now I know that the two things which will be removed from the heap are, the two nodes will be C and D nodes. So now what I need to do is, I will create a new node. So let's say this is my new node now. And for this new node, I will not specify any data. It could be any data, like it could be a null character or any character. And but it's the new node's cost will be the sum of the costs of the two nodes which are being removed from the heap. So the two nodes which are removed are 2C 8 and D 2, because it was a min heap. So two smallest values are removed first. So the total cost of this new node will be 10, which is the sum of these two costs. And the character could be anything. It could be a null character, it could be anything of the new node. And on the left, it will have a node C, or in the right, it will have a node D. It could be on the left, it could be D, it could be right, C on the right. But let's say on the left, it will be having this node C. So this new node's left will contain the C node. Its data was C, its cost was 8, and its left was null and its right was null. Similarly, on its right, it will have a node D on its right, its character is D, its cost is 2, its left is null, its right is null. So this is how we will be having this new node being formed. Now what we will do is we will insert this node in the this heap. So now the updated heap will now be, so updated heap will have A, there will be now 3 nodes, one will be A 60, left null, D null, right null, sorry, and then in this node we will be having a node B 30, its left null, its right null, and now we are having a third new node. So C and D was removed. This third node is having its character, like let's say it is a null character and its cost is 10, and it further has a node C and D on its right. So C and D you can imply from, you can see what is the C node and what is the D node, as this structure is being formed here also. So it will be having below it will have here the C node, and on the right it will be having the D node, as you can see here. Now this is my updated heap. Okay, but as we know that we need to loop through this heap until the size remains 1. So now the size is still not 1, it is 3. So we will again pick out the two smallest value, and this time we will get, let's say this is the node CD now to denote, because it is a combination of node C and D. Now the two nodes which will be removed from the heap will be CD and B. So it will be B and CD. So B's cost is 30, CD's cost is 10. So now we will again form a new node. So this new node will be formed now. And its character could be again a null character. We are not considering here character now. We are more interested in the frequency or the count. So its cost will be the sum of these two costs, that is 40, and on its left it will be having the node B now. So it will be having a node B. So B, its cost was 30, its left is null, its right is null, and on its right it will be having a node now CD. So the CD node was my this node. So its character is a null character. Its cost was, so CD's cost was, we had 10, and on its left we had a node C. So I am just creating the structure again to elaborate so that you are not confused with how this thing is working. So C, and its cost was 8, its left was null, its right was null, and now D, its cost is 2, its left is null, and its right is null. So we are having this thing. Now we will insert this node inside the our heap again. So now the updated heap will be again, it will have two nodes. So one node will be the A node its character as A, its cost is 60, its left is null, its right is null, and 1 will be this node. Let's call this node as BCD. So it is a combination of B, C, and D. So this entire node. So this is its character is a null character, its cost is 40. So yeah, its cost is 40. On its left it is having a B node, and on its right it is having a C node, CD node, and CD is further broke down as you can see here. So you can see this picture for this node here. So this is a node BCD, let's say. Now this is my updated heap after looping, but still the size is not 1, so the same step will be repeated again. So this time I will explain quickly. So again we will just remove the two nodes. So this time the two nodes which will be removed are A and BCD node here. So I will be forming a new node now. So by this new node is being formed, and its character is a null character. Its cost will be the sum of these two costs, that is 60 and 40. So 100, and on its left I will have a node A, and on its right I will have a node BCD. So, and this thing will be inserted into the heap. So my updated heap will now have only this node, only just one node, and its size is 1. So we will not repeat this step again. Now let's see the entire heap, what we will be having inside our entire tree structure of this heap now. So at the top I will be having this thing. We will be having a null character, its cost as 100. On its left I will be having a node A, its cost as 60. Its left is null, its right is null. So this node's A node's left is null. This is my A character's node. Its left is null, its right is null. This is my A node here. And on its right I will be having the node BCD, and for this BCD node what I will be having is I will be having this null character. Its cost was, let me see, so BCD, its cost was 40, and on its left it had, so this is my BCD node. So on its left I had a B node, and on its right I had CD node. So B node, so its character will be B, its frequency was 30, its left was null, its right was null, and this is my CD node now. So this is my CD node. So its character is a null character, its right value, its cost is 10, and on its left we will be having the C node, and on its right we will be having the D node here. So here the two nodes are also present, which is the node C and node D. So this is my node C, its cost was 8, its left is null, its right is null, and this is my node D. and D. So its cost was 2, its left is null, its right is null. So this is my entire heap structure which is being formed now. So what we need to do is, so we need to remove this last node, so which is appearing in this way. So this last node is visible as this way, so I have elaborated here. Now what I will be doing is, my next step will be, which is my fourth step here. So yeah, first, second, third and fourth step. Now the fourth step is retrieve the last node. So I have taken out the last node and I have also expanded it here only. So this is the last node, how it will look like. So retrieve the last node. So let me write this thing on the top only, so it will be better to explain. So this is the fourth step, retrieve the last node. So I have opened up the last node in the form of a tree here. And now what I need to do is, fifth step is parse the tree to fill encoder and decoder. So this is my fifth step. So how we will just do the pre-order traversal of this tree, and whenever we will be moving towards left, we will be adding a 0, and when we are moving towards right, we are just adding 1. So we have started from this node, we have moved towards left, we have added 0, we have moved towards right, we have added 1. Again left, we have added 0, again right, we have added 1. Now again left, we have added 0, and again right, we have added 1. Okay, so now as you can see, all my leaf nodes, which is this node, and this node, and this node. So all my leaf nodes are nothing but just the characters of my string which I had. So my string just consisted of 4 characters, and those 4 characters were A, B, C, D, as I just made a frequency map of those. And this final node which I got, the tree structure which I got for this final node, in this tree structure all the leaf nodes are nothing but just my characters only. So now what we will do is, as we move towards left we will add a 0, as we move towards right we will add a 1. So now my encoder will look like for A. So let's see how my encoder and decoder will look like. So A, B, C, D, this was my encoder, as we use this same thing above also. So my encoder, so this is my key, the character, and its value will be a string. So for A, what we will have is, we will just have a string 0 as its encoded value, because we just moved towards left, we encountered A, so its string will be 0, its value. For B, what we will have is, we know that we need to reach B, so we have moved towards 1 and then 0, so it is just 1 0. Now for C, what we will be having is, we will be having 1 1 and then again 0. And for D, we will be having 1 1 and 1. So 1 1 and 1 to reach the D node. So this is how my encoder will look like. Similarly, my decoder will look like. So my decoder will have these same string values as the key now here. So 0, 1 0, 1 1 0, and 1 1 1, and the values will be A, B, C, and D respectively. So this is how my decoder will look like. So this is my key string, and its value is the character. Similarly here, this thing is my string as value and key as a character. So this is how my encoder and decoder will look like after passing this tree. Now the sixth step is, let's see how these values will be encoded. So let's say I had my original string as, or I had a string A B B C C D A. So I had this string of 7 characters. Now, as we know, there are 7 characters and each character will be taking 2 bytes. So there will be total 14 bytes into 8 is equals to 112 bits. This string will be taking up space inside the hard disk. We will be storing the string in the file. So it will be taking 112 bits. So now if I will use the Huffman encoding technique, what I will do is, for A I will add just 0, for B I will add here, as I can see, 1 0, and for another B I will add this 1 0, for C I will be adding 1 1 0, and again C I will be adding 1 1 0, and D 1 1 1, and A is again 0. So this is how this string will be stored inside hard disk in the encoded format in my memory. So these zeros and ones are nothing but just only bits. So initially here they are strings, but at the time of storing in the file we will convert these strings to the bits, so that later on the only bits are being stored on the file. So this will be taking space 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So it is now taking the space only 15 bits as compared to 112 bits now. So I hope you are clear with this thing, how we have saved the lot of space now. From 112 bits, it is now just taking only 15 bits because we are just storing the string in the form of zeros and ones. So this is the Huffman encoding. Now, when we will be reading this thing from the file again, now let's say how this thing will be read as. Now it could be 0 0. So for 0 we will say we had in the decoder we had A. Now here 1. So for 1 we had nothing. Now again 0. So 1 0 is the combination and we had B here. So for this string we had a B. Now let's say it could also have been like 0. If it could have been like 0 1 0, if the value for any character could have been like, for let's say for A we had a 0 and B if we had 0 1 0, then it would have been very difficult to identify what we are talking about. So whether this will be A, this will be kind of, let's say, A, and now this is A or this is B. So it would have created a lot of confusion and the concept would have gone wrong. But the tree which we are building above here is making sure that none of the value which has occurred earlier is the prefix of the other value. So for an example here 0, 0 is not prefix of any value here, and 1 0 is not a prefix of any other value. Similarly 1 1 0 will not be the prefix of any other value. So this thing will help us to retrieve the data from the file and read it in a better manner while decoding it. So 0, for 0 we have A, 1 0 we have B, again 1 we have nothing, 1 0, okay, now again 1 0 we will have B, 1 we have nothing, again 1 we have nothing, 1 1 0 is our C. Similarly again 1 1 0 will give me a C, 1 will give me nothing, 1 will give me nothing, 1 will give me nothing, but this 1 1 1 combination is a D. Now again 0 is present, it will be my character A. So this is how now I will retrieve the value. So I hope you are clear with this thing. This is how the Huffman encoder works and how the encoding is done and how the decoding is done. In the next video we are going to see how to code this thing. So thanks for watching this.